Look, if you've ever stared blankly at a physics problem and just felt totally lost, trust me, you are definitely not alone. But don't worry, we're going to break down all the big ideas right now, step by step. By the end of this explainer, you're going to walk into that exam room feeling super confident and ready to tackle absolutely anything they throw your way.
Here is our game plan for today. We're going to start with vectors versus scalars, move into Newton's laws in action, figure out making sense of momentum, review the essential exam equations you need, and wrap up with the top physics exam pitfalls to avoid.
All right, kicking things off with part 1, vectors versus scalars.
So think about it like this. All our measurements in physics basically fall into two distinct buckets. You've got your scalars, which literally just have a size or a magnitude. A distance of 10 meters, that's just a scalar. But then you have vectors. These guys must also have a specific direction attached to them. So displacement is distance times with a direction, like 10 meters north. It's the exact same deal with speed versus velocity. And pay special attention to this one. Mass is just a scalar, but weight is a force acting downwards due to gravity, making it a vector. Always keep that distinction in mind.
Moving right along to part 2, Newton's laws in action.
Okay, Newton's first law. This one basically says that objects are kind of lazy. They like to keep doing exactly what they're already doing. If it's sitting still, it's going to stay still. If it's moving, it's going to keep moving at a constant velocity. So the absolute crucial point here is that a constant velocity simply means the forces acting on the object are perfectly balanced. They cancel out, creating a zero resultant force. No extra force means no change in movement.
Picture a skydiver jumping out of an airplane. It is the perfect everyday example of this. Initially, their weight pulls them down, so they accelerate toward the ground. But as they fall faster and faster, the air resistance pushing up against them increases. Eventually, that upward push perfectly equals their downward pull. The forces completely balance out, the resultant force drops to zero, and the skydiver stops accelerating. They just fall steadily at what we call terminal velocity.
But wait, what happens if those forces aren't perfectly balanced? Well, enter Newton's second law. An unbalanced force, a resultant force, actually causes an object's velocity to change. It makes it accelerate. And the famous formula, F equals ma, tells us exactly how that works. A bigger push or pull means a bigger acceleration, but if the object is really heavy, meaning a larger mass, you're going to get a much smaller acceleration.
You know that required practical with the trolley on the track? You're almost guaranteed to see an exam question on this. You've got a trolley pulled by a string that's attached to falling slotted masses. As you move those little masses from the trolley over to the hanging string, the pulling force goes up and the trolley accelerates faster. But listen closely, here is the trick examiners absolutely love. You have to keep the total mass of the entire system constant. You take the mass off the trolley and put it right on the weight hanger because the force of gravity is accelerating both the trolley and the falling masses together.
All right, on to Newton's third law. It states that for every action, there is an equal and opposite reaction. But be careful here. This is the law that confuses students the most. You really have to remember it's all about the interaction between two entirely different objects, not balanced forces acting on a single object.
To really visualize this, imagine two ice skaters standing face to face on the rink. If one skater pushes the other, they don't just stand perfectly still while their friend slides away. No way. The person pushing feels the exact same force pushing back on their hands. They both feel the exact same size force, and because ice is super slippery with very little friction, they both recoil and slide away in opposite directions. Equal force, opposite direction. Two entirely different objects. Makes sense, right?
That brings us to part 3, making sense of momentum.
So what actually is momentum? Simply put, it's just mass multiplied by velocity. Think about it. A heavy truck moving really fast has a ton of momentum, but a tiny bug sitting on a leaf? Zero momentum. And because momentum relies on velocity, which we know is a vector, momentum itself is a vector quantity. Direction matters immensely. And the golden rule here? The law of conservation of momentum. In any closed system, the total momentum before collision always exactly equals the total momentum after.
Let's make this super concrete with another everyday analogy. Picture a heavy bowling ball barreling down the lane towards a completely stationary pin. Before the impact, only the bowling ball has momentum. The pin has zero. Bam! When the ball smashes into the pin, it transfers some of that momentum over. This is conservation in a nutshell. As the pin gains momentum and goes flying backward, that heavy bowling ball must lose momentum and slow down. The total momentum of the ball and the pin together after the crash is exactly the same as the ball rolling all by itself before the crash.
Okay, part 4, essential exam equations.
First up is the absolute classic,
F equals ma. This is your go-to formula for Newton's second law. Force equals mass times acceleration. A huge tip for the exam. When using this, always make sure your mass is in kilograms and your acceleration is in meters per second squared. If they try to trick you and give you the mass in grams, you've got to divide by 1,000 first.
Next up, we've got P equals mv. That's momentum equals mass times velocity. Now remember what we said about vectors earlier? Because velocity is a vector, your momentum will actually become a negative number if the object bounces off something and travels in the opposite direction. Always track those positive and negative signs when you're doing collision calculations.
And here is a slightly trickier one, tying force and momentum together. Force equals the change in momentum divided by the time it takes. This equation right here perfectly explains modern car safety features like airbags and crumple zones. Think about it. If you're in a crash, your change in momentum is a fixed amount. You're going from driving fast to a dead stop. But by inflating an airbag, you increase the time it takes for your head to actually stop moving. Dividing by a bigger number for time means you drastically reduce the force felt by the passenger. It's a classic exam question, so definitely lock that explanation into your memory.
Finally, let's wrap up with Part 5, Top Physics Exam Pitfalls.
Let's make absolutely sure you don't throw away any easy marks by looking at examiner pet peeves. First up, when you're calculating weight, little g is not gravity. Gravity is the overarching concept. Little g is the gravitational field strength. Be precise. Second, never write that a distance gets faster. A time gets shorter, a speed gets faster, but a thinking distance increases. Third, like we just warned, do not ignore your negative signs in momentum if an object changes direction. And lastly, examiners really hate what they call Tarzan speak. Don't write heat liquid with fire. Write like an actual scientist. Heat the water gently using a Bunsen burner. The whole point here is precision in your language. So, with all that in your back pocket, are you really going to let the examiner catch you out on those simple mistakes? You've got the tools, you've got the analogies, and you know the equations inside and out. But remember, beyond just passing a test, these exact same laws govern literally everything around us, from a falling apple to a rocket launching into orbit. So the next time you step on the brakes in a moving car, ask yourself, what invisible forces are actually working together to keep you safe? Good luck on your exam and keep questioning the physics all around you.